Hello, I've got a project for my Apple II Plus. I'm going to be replacing all the ROMs in it with one EPROM. And my motivation for doing so is that while the Apple II was a marvel of engineering, one of the double-edged sword design decisions was putting everything, all the chips, in sockets, which is great for replacing bad chips. But the downside is that over the decades, those connections between the chips and their sockets get contaminated with oxidation and corrosion and spiders and dust and whatnot. And on my Apple II Plus in particular, I've noticed that it's the ROM chips that are particularly prone to this. And I've tried to pull the ROMs out so that I could clean them with some contact cleaner, and broken off pins because the chips are so tight in the sockets. So I've had to patch it together with wire, and I'm done with that. I'm going to do it right. I'm going to replace everything with one EPROM. And this video is going to show you how to do that. Okay, so let's see what we're up against. On the main board, there are 6 ROM slots that hold the Applesoft BASIC and a monitor ROM. And the Apple II Plus came with this other card that plugs into the peripheral slot that has the Apple Integer BASIC code set on 3 of its ROMs. It has a programmer's aid on one, comes with its own monitor, and there's one empty slot. Now, we could go in and replace each of the 2K ROMs with a 2K EPROM. It's not quite as straightforward as we'd like because 2 of the pins are not pin-for-pin compatible. One of them, the VPP pin, just needs to be tied up to 5 volts, and that's fairly easy to do with a single wire. But the other pin, the active low output enable, is a pain because the original pin on that socket is an active high signal. So we have to introduce an inverter somehow, either with a discrete chip or a transistor. But either way, it's kind of a pain. People have done this. Here's a picture of a mod somebody did. You can see the 2 pins on the EPROM have been pulled up and wired to, and there's an inverter chip up on end at the top of the EPROM there, and more wires, and it can be done. If you were to do this on all 6 of the ROMs, you don't need to duplicate the inverter, but you do need to take the output of that inverter and daisy chain it over to all 6 ROMs. And that has been done as well, and it looks as you would expect it to. We shouldn't have to do that because we're just going to take all the 2K ROMs and reprogram them into one big ROM, EPROM. The 27256 is a 32K byte part. So it has enough room to store the entire Integer BASIC ROM set in its lower half and the Applesoft ROM set in the upper half. This mod will require a few extra address pins, more than go to the ROMs themselves, which only have address 10 down to 0. We need 14, 13, 12, and A11 as well. So those are not readily available on the main board, but they are on the peripheral slot. So that's where we're going to do all our work. That has all the pins we'd ever need to do this. Now we could go off and buy a blank board on eBay for 10 or 12 bucks. These boards are available. They fit right into the peripheral slot, and we could take our EPROM, solder it onto this board, solder 28 wires over to the appropriate pins, add our chip select logic, and that would work. But we're going to take a far easier route. Because we're an Apple II Plus owner, we have this integer card. And you'll notice that on this card, in addition to the 6 ROM slots, there are a couple extra chips. And what it turns out what those chips do is produce pretty much all the signals we need to do the mod we're talking about. And so in the rest of the video, I'm going to go into the detail what those mods are. And we're going to end up with by hacking this board a little bit with a few cuts and jumps, and going to end up with a system that replaces all the ROMs on both the integer card and the Applesoft ROM with one EPROM. And we're going to maintain the functionality of the switch on the back to select between Applesoft and Integer BASIC. So if you're ready, here we go. We're going to dive in to the rework. Okay, so here's the schematic of the Apple Integer BASIC card. There's the 6 ROMs along the top. The chip select logic on this card is very similar to the logic on the main board. It's centered around this trusty 138 decoder that generates one of 8 chip selects on its output, active low, under the following conditions. The upper address lines of the processor, A15 and A14, both have to be high, and that puts us in the upper quadrant of the address space from C1000 to FFFF. The read-write line needs to be high to indicate we're reading from the ROMs. And this signal is a clock, phi1, that has to be low. And there's a DMA signal that has to be high. If all those conditions are true, then these two enables are in the correct situation to enable the 138. We'll talk about this last one a little bit later. But assuming that all the enables are true, the encoder then looks at these 3 address lines and decides which of these 8 signals go low. And if those are going to these chip selects, we're selecting one of our 6 ROMs on this board. Now, if none of those are selected, then this 138, all the outputs are inactive. They're sitting high, which means all these AND gates are high. And the output is high out here. This is the inhibit signal that goes back to those active high chip selects on the main board, Applesoft ROMs. So if it's high, they're enabled, they're not inhibited. But if we want to access a ROM on this card, then we bring one of these lines low, say this one, and that'll bring this AND gate low. And this particular AND gate's a special one. It's called an open collector AND gate, which means if any of these AND gates go low, this entire net goes low. And that brings the inhibit line low, which will cause the Applesoft ROMs on the main board to be inhibited. Instead, we'll get one of these ROMs. So that's great, but we don't want 6 individual chip selects. We want 1 chip select for the entire card. So it turns out that this signal at the output of the AND gates is exactly what we need. It'll be high normally, but if any of these 6 EPROMs get selected, then it goes low. That's exactly what we want. That in fact becomes our active low chip select that goes low if we're in that 12K byte address range. So we're just going to take that chip select and route it right into our chip select pin of our new EPROM. Then all we have to do beyond that is wire up the upper address lines, A11 through, 11, 12, 13, and 14. And we're just about there. Okay, now let's talk about this last enable. This chip here is a flip-flop, 7474 flip-flop. And it's responding to the switch on the back of the card. And it looks at the reset signal from the main board, which happens when you press that spring-loaded button on your keyboard. When that's pressed, depending on the setting of the switch, this flip-flop will either reset or set. And so this Q line will either go low or high. And if it goes low, that enables this 138, and we're using this card, the Integer BASIC card. But if it's high, then this whole 138 is not enabled, and this card doesn't do anything. And we're using the ROMs on the main board. So in our case, we don't want this mechanism to switch. We're only ever going to be using this one EPROM, so we always want the logic on this board to be active. So we need to take this active low enable and make sure it's always enabled. We can do that by tying it low, which would be pin 8 of that 138, or what I've chosen to do is just tie it right up to pin 4, right next door, pin 5 and 4, because pin 4 is also an active low enable. And we need to cut the trace that goes back to the flip-flop. So now this is always enabled. But we're still going to use this flip-flop output that's going either high or low depending on the setting of the switch. And we're going to use that simply as our upper address line of the EPROM. So what that's going to do is our EPROM, we draw it over here, we're going to cut it in half, and the lower half is going to be the integer basic, and the upper half is going to be the Applesoft, and it's the A14 line that selects between the upper half and the lower half. So there's a few other little details that will make the rework a little simpler, and I'll go into those on the next slide. Okay, here's the complete schematic of the operation. I've drawn the new EPROM kind of over the top of the second ROM slot on the schematic because that's the empty socket. Over on the right, I've shown the pin differences between the original ROM and the new EPROM. The new EPROM is a 28-pin part. It's going to go into the old 24-pin socket with 4 pins overhanging the edge. And I'll show you how I did that without resorting to soldering to the actual pins of the EPROM. So the rework involves, we need to take these 3 address pins, A11, 12, and 13, and wire them over to the EPROM. Those are readily available right at the 138, pin 1, 2, and 3. A14 comes from the flip-flop, like we talked about. And to get that to work properly, we're going to need to cut the trace from that flip-flop to the 138's pin 5 enable and wire pin 5 over to pin 4. The chip select output enable of our new EPROM is coming from our magic AND gate tree. And a couple other things. Since we're putting this EPROM into the socket of the second part, that has the original chip select on its pin 20. Here it is over here on the right. It's pin 20, which now maps over to our new pin 22 output enable. So that would be a conflict if we left that trace connected to the 138. So we need to actually get in there and cut that trace. And now the only thing driving that pin will be our new chip select. Another pin we're going to play with is this one. Pin 18 of the original ROM set is an active high chip select. And what they did on their board is they just tied them all high with this pull-up resistor. For us, the pin 18 of the original chip select is now mapped over to an active low chip select. So conveniently, Apple provided for us this mechanism on the board to just short out that node to ground if we want to. There's 2 pieces of copper right next to each other that you can just put a solder blob across and ground that node. And at that point, we've disabled all the ROMs on the integer card. And so we don't need to physically remove them anymore. Yet for us, the ROM we care about, that pin 20, that pin 18 is an active low, so that's what we want to do. We're tying our active low chip select low. And the only chip select we're going to actually need is via the output enable. So the chip select's low, and we don't have to wire anything over to it. It just happens for free by shorting out this node. The last thing I want to do is the pin 21 of the original ROM, which was an active low chip select, that what they just wired it permanently using this pull down resistor R2. In our world, that's now an address pin A11, which we're wiring separately. And since we don't want to lift the pin, it's going to still be connected to this node here. Let's just remove the resistor so A11 doesn't have to drive a 3K resistor to ground. And so by removing that resistor, it's just floating, and that entire net will now be driven by the A11 net, which we need for our ROM, and as a don't care for the other ROMs, which are disabled anyway. Let's see. The last thing it looks like is the top 2 pins of the EPROM. There's the power pin, pin 28. It certainly needs to be tied over to 5 volts. And pin 1 is a VPP pin that also needs to go to 5 volts. Just one last detail. On the board that I'm going to rework, I'm going to actually use a 27512 EPROM, which is even twice as big. And just because maybe someday that gives me 2 more quadrants to put code into if I ever choose to. And in that case, pin 1 becomes the next address pin, A15. And I'm just going to tie it low on my prototype. But if you ever want to use this, you would tie it over to yet another switch. And that would give you 2 more ROM contents to play with. You could switch between Applesoft, Integer, and then 2 other versions of your own choosing. And so I just left that facility in there in case I ever want to do that by putting a 512 in there. And I'm not going to put the switch in. I'm just going to tie that line low. So how ugly is this rework going to be? Here's our integer card. And I'll show you the 3 cuts that need to be done first. First is the cut between the flip-flop output and the 138. It's a nice topside trace, easy to get to. Then the pin 24 power pin of the original ROM needs to be cut on its way to the power plane. That's a big thick trace, very hard to cut with an X-Acto knife. If you have a better tool, use it, but it can be done with diligence. And then turn the board over. This is the ROM again, the original pins 24, 3, 2, 1, 20. And that's the output enable pin. We're going to cut that long trace that goes back to the 138. So we'll need a socket, preferably a 28-pin socket. But I couldn't afford a 28-pin socket. It was like $2 plus $8 shipping from DigiKey, so forget that. I went down to my local electronics store where they only have 24-pin sockets. But you can get 2 for $2, and with a little mechanical ingenuity, it is possible to make a 28-pin socket. Cut them down to size, get 2 14-pinners, kind of sort of glue them together, and you too can have a 28-pin socket virtually indistinguishable from the real thing at a fraction of the cost. Perfect fit. Then when we put it into our card, it's going to overlap by 4 pins, and the 4 pins of the socket are going to be accessible to solder to. So we can go down on and solder to the socket pins and not to the EPROM itself. Okay, let's start up at the corner of the board with the 2 resistors. R2, we're just going to remove completely. R1 goes to a solder pad that's right next to another solder pad, and we're just going to blob those together with some solder, which connects R1 to ground, which is what we want. Then we are going to do the chip select to our new EPROM. That comes from pin 3 of the AND gate of the LS09. So pin 3 on the bottom of the board, over to the old pin 20 of the ROM, which is our new pin 22, and we'll do the trace cut back to the 138. So there's our wire, and there's our cut. Then we'll go to the 138. Pin 1 is where the address bit 11 is, and we'll wire that over to the old pin 21, which is the new pin 23. You got to keep your head on straight a little bit when you're looking. Make sure you got your pin numbers right. There's pin 1 of the EPROM, but that on the bottom of the board it's not there. It's 1, 2, down to 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 of the new pin out. Then we'll do pin 2 of the 138. That's the next address line. That goes over to the pin 2 on the EPROM, which is hanging off the board. So I wired it through a spare hole on the board just to keep it somewhat neat. And that comes over and solders to the socket that's hanging over to pin 2. Then the next one is the pin 3 of the 138, which is the next address line. That goes over to the old pin 24, which is the corner pin on the bottom of the ROM. Next, the Q of the flip-flop, which is pin 9, 7, 8, 9 of the 7474, that goes up to the new pin 27 hanging off the edge of the board. So that also went ahead and routed that through the spare hole on the board. Okay, then we're going to do the cut on the trace that goes from the flip-flop over to pin 5 of the 138. And then we'll short out pins 4 and 5 on the 138 on the bottom of the board. So there's the cut on the top. That's very convenient. On the bottom, we short pins 4 and 5, and you can see that I screwed it up and shorted 5 and 6. That's not going to work. It needs to be 4 and 5. So I didn't redo the video, but you get the idea. Lastly, there are the 2 corner pins of the EPROM. Pin 28 is power. That goes to, there's a power pin on that decoupler, C5, right there. And pin 1, you'd also want to go to the power pin if you're using a 27256 that has VPP on that pin. If you're using a 512 like I am, I wired it to ground. So here's the extent of the damage on the top of the board. Not too bad visibly. And then the bottom of the board has a few wires. That's what it looks like. And that's it. That's the complete rework. We're done. And the 28-pin EPROM just goes into that socket, and Bob's your uncle. Okay, I suppose you're going to make me prove that it actually works. So I took out all the ROMs from the main board and the integer card. You can see how bad some of these ROMs are. That one came out of the main board, had a broken pin, had solder blobs to connect broken pins together. It was a disaster. So I'm going to plug it in, test it out in both switch positions. Starting out down, that's the integer Applesoft mode. Turn the power on. There's Applesoft. And flick the switch up, and it comes up in the integer basic mode. So there you go. Okay, just one more thing very quickly. Remember, the integer card had one empty ROM slot. That gives us the opportunity to add our own code there for our own purpose. And what I was thinking is adding a RAM test, a power-up RAM test, because the 24 RAM chips on the board are also similarly susceptible to failure due to dirty contacts. So I wrote a quick little test that will pinpoint which RAM fails. RAMs, the 24 RAMs in this white box. Let's refer to them as 3 banks of RAM, 1, 2, and 3. This lower bank starts at address 0. The second bank is at 4,000, and the third bank starts at 8,000. And let's number these RAMs 1 through 8. So what this RAM test does, if it finds a failure, say in this RAM here, it'll beep the speaker twice to denote the bank, and then 7 times to denote the which RAM in the bank. Taking out this RAM right here to make it fail. It's in the third bank, 6th RAM over. Turn the power on. Okay, thank you for everybody in the world who's watched this video till the end, both of you. There's a website I set up with the necessary information for this, the EPROM images and such, and some documentation, and a contact address for me if you have any comments or corrections, improvements, aspersions, cast them to there, and I'll get back to you. Thanks.